All right, we're starting in on the next topic, which is energy. I did end the last lesson on momentum and impulse, realizing that there was one bit that I wanted to show. I'm going to show that now before we get started with energy. The idea was that F delta T is called the impulse, and that it's equal to the change in momentum. And I had shown that the slope of a momentum versus time graph, when two things are colliding, the slope is the net force during the collision. What I failed to also show was what the area of a force versus time graph represents. So if someone also gives you the force versus time graph for two things that are colliding, let's say it looked something like this. I don't think it would for an actual collision, but this is an example to illustrate an idea that this product, F times delta T, is equal to the impulse. So if you were to break this down and recognize that there are areas in here, if they asked you what was the total impulse pulse, this was 0 seconds, 5 seconds, and this was 10 seconds, then there's a certain impulse occurring during the 0 to 5 second period, and that impulse is this area. And so impulse is area of a force versus time graph. And so all you'd have to do is just pick out the shapes. Looks like this is 5 seconds wide since it goes from 0 to 5. And they would have to have given you some value up here. Let's say they said it was 20 newtons. So the force is increasing up to 20 newtons. And 5 seconds later, the force is finally 20 newtons. And then it maintained a 20 Newton force for the final 5 seconds from 5 to 10 seconds. So this would be 20 newtons high. And this would be 1/2 base times height, since it's a triangle, because base times height would just be the area of the rectangle, and it's half of that, right? And so it would be 50. It would be 20 times 5, 5 times 20 times 1/2, and you get 50. And so that means the impulse during the first 5 seconds would be 50 during this area. And then to find the impulse during the 5 to 10 second mark, you would draw another square and see that it's also 5 seconds wide and 20 units high. And so this would have an impulse of 100 units, and therefore the total impulse would just be the sum of those two areas. It would be 50 plus 100 would be 150 units. All right. So now that closes that section out. Let's move on to energy. There are two types of energy, primary types of energy. And those two types of energy are either potential energy or kinetic energy. Kinetic energy is motion energy, and potential energy is some form of stored energy. Okay, so kinetic energy is 1/2 mv squared, noticing that k is proportional to v squared. So if the velocity of an object doubles, kinetic energy goes up by 2 squared, which is 4 times as much kinetic energy. The potential energies that you're most often concerned with at AP Physics exams is the potential energy symbol is U. The gravitational potential energy is mgh. So if there's some block, sitting up at some height, say 5 meters high, you would need to know what it weighs, remembering that mg is weight. And so the potential energy of this object up here, if you were given a mass, would be 2 times 9.8 for g, mg, and you'd have to plug in h of 5, and you could compute its potential energy. That's gravitational potential energy. It's a stored energy. that often comes out and turns into kinetic energy if you release the object from that height. Note that it's linear, so a doubling of height doubles your potential energy. And if someone asks what a graph looks like for U versus H, it would just be linear, because the model for that data is they're both raised to the first power, and mg would actually be the slope. Slope is the weight of the object. The other kind of potential energy that is most commonly turning up is elastic potential energy, at least turning up on AP exams. So before I can go into elastic potential energy, let's do a quick review on springs. So Hooke's law is the law that says that when you pull on a spring, if a spring looks like this, and then you pull it out by applying a downward force, it will elongate, and this is known as its elongation, delta L. Physics books sometimes just write delta X for how much its length changed by. And Hooke's law is the idea that the force that you use to stretch a spring is proportional to how much it actually stretches. Note that when you're applying a force downward, if you were holding it there in this position, the spring would have to be applying an upward force that's equal to your applied force so that they cancel, so there's no net force if you're in fact holding it in that position. So the spring force is proportional to how far you stretch it. So if you stretch it twice as far, the spring force will pull back with twice as much force. And the spring force is also proportional to the stiffness of the spring, which is called the spring constant. For springs, and its units are newtons per meter. So if the spring constant of a spring is 5 newtons per meter, it means if you stretch, go over to that spring and stretch it out by pulling on it with 5 newtons, if it actually is a spring that has a spring constant of 5 newtons per meter, and you apply 5 newtons of force to it, it'll stretch by 1 meter. If you applied 10 newtons of force to it, it'll stretch by 2 meters. If you applied 2.5 units of newtons of force, it'll stretch by half a meter. And so the spring force is a combination of those two, and when you graph it, as is typically shown, the spring force versus elongation is linear, and the slope would be k. So it turns out that when you stretch it out, you do work, which I guess I can do a little side lesson on work right now. Work is a force times a distance times the angle between the applied force, or whatever the force is that you're interested in determining how much work it's doing. And theta in the cos theta is the angle between that force that you're interested in and the direction of motion. D is the displacement. For lots of problems, theta is 0 degrees. For something like pushing a block, if it goes from point A to point B, then the displacement vector would just be from there to there. There's a displacement vector. And if you're applying a force to the right while it moves to the right, then those two vectors are in the same direction. There's the applied force, and then the object sliding like that. And those two angles are in the same direction, so theta would be 0 degrees. And when you do cos of 0 degrees, that's just 1. And so in a lot of cases, not all cases, but in a lot of the simplest cases, work ends up just being a product of force and distance if theta equals 0 degrees. So it turns out when we apply that, it takes work to stretch a spring because you have to apply a force over a distance. And so in the physical picture, here's your spring, and then you decide to stretch it out, you will have displaced the edge of the spring downward, and you will have to have applied a force in order to do that. And since those are in the same direction, the work that you'll have done in stretching that spring is equal to the applied force times the displacement or stretching of the spring, which could be referred to as delta x. So when you recognize that work is also the area on a graph for force versus distance. So if you have a graph of any graph of force versus distance, and for stretching a spring, Hooke had claimed that it would be linear, then what we recognize is if we stretch it out up to this distance here, the area of this curve here represents how much work we've done, because work is equal to the product of a force and a distance. And so you have a triangle in there, and you'd say that it's the spring force is what we're measuring here, and the displacement that you've stretched the spring is going this way from here to here, and therefore from a geometry standpoint, finding the area, force times distance, oh, that must be work. So work is the area. It's an important idea. Work is the area of a force versus distance graph. And if it happens to be that we're interested in how much work was required to stretch the spring, this value up here is whatever the highest spring force you felt as you stretched out this spring. Remember, you'd have a spring, you stretch it out, and this is the data that you collected for how much spring force you felt on your hand as you stretched it out to a distance d. And the spring force is always equal to K times delta x based on Hooke's law. And so if you're doing this as an area problem, the height of this is K delta x, and then the displacement you can think of as just delta x from here to here. So when you end up finding out the area of it, of that triangle on the right side of the screen, the area would be K delta x times another delta x, right? K delta x high by delta x wide, and that comes out as K delta x squared. But then you recognize, oh, it's a triangle. It's only half of the area of that whole rectangle, so you'd have to multiply that by a half. So this is the work equation to stretch a spring. Depends on how stiff the spring is, K, and it depends on how far you've stretched it, delta x. If you stretch it further, it's going to take more energy for you to stretch it that further distance. Specifically, if you stretch it twice as far, delta x would be twice as much, and the work would be 2 squared, which is 4 times as much energy to stretch that spring twice as far. But because of the conservation of energy, it states that you can't make energy vanish out of the universe, and you can't create energy from nothing. That energy can only be transferred from one thing to another, like momentum and the conservation law for momentum. It means that when you grab a spring and stretch it, energy is being transferred from you to the stretched spring through the process known as work, because work is a process of transferring energy. And so since the work required to stretch a spring is 1/2 K delta x squared, it may not be a huge surprise to recognize that the potential energy stored in a spring is that same equation, 1/2 K delta x squared, which brings us back around to the other kind of potential energy that is very commonly referenced in an AP Physics 1 exam. Remember, we started with describing different energies. It described the potential energy that was gravitational potential energy, which was mgh. And now there's a spring, which is called elastic potential energy, which is 1/2 K delta x squared. Okay, and then another comment is, how do you find the spring constant? Well, often what you would do, and at least the way it's depicted in AP exams, and it's a pretty easy experiment to do, I've done it with you students of mine, you would measure the original length of a spring, right? You call that, let's say, L1. Then you hang something from it. You measure its length. You call that L2. You find out how much it stretched from here to here, would be called delta x, which would be L2 minus L1, which is the extra length there. And you'd have to recognize that it's an equilibrium in this hanging condition, that the spring force is pulling upward with an equal amount of force as the weight. And since we know weight is mg, and the spring force must also be mg. Technically, this would be negative, and this other one up here would be positive, right? And so if those forces are equal while it's hanging in equilibrium, you state that by saying the spring force equals Fg. And then you would just stick in Hooke's law definition for the spring force. The weight is mg, and you can solve for k now. K would be mg divided by delta x, where mg is the weight of whatever the object is that's hanging here, has some mass. Multiply that by g, and it's its weight. And delta x in the denominator right here would have to be how far it's stretched. The elongation, the difference in its length after it was stretched. That's how you'd solve for k. The next quick thing I'm going to go over would be the conservation of energy, and showing you that that's a very easy method to use for solving a lot of problems where something is falling and its potential energy is decreasing and its kinetic energy is therefore increasing. It's speeding up as you speed up as you fall. As you're closer to the ground, potential energy drops, and that loss of potential energy turns into kinetic energy. So some of the simple problems that turn up would be, let's say a ball starts here at rest, V initial equals 0, and then you want to know how fast is it moving at the bottom of the ramp. Well, you can't use the kinematics equations because those are all constant acceleration equations, and you wouldn't accelerate at a constant rate when you're on a slope that looks like a curve. You would accelerate very rapidly at first when mg sine theta, the component of your weight pulling you down, is really large, and then because right here this would be a large component of weight, and then as you go down this ramp, that component of weight would get smaller and smaller and smaller, because the angle is approaching 0 degrees. And so since that gravity force component is getting less and less and less, that means that the force you feel is not constant as you go down this slide. It's dropping, it's decreasing. And since acceleration is proportional to force, your acceleration, if your force is dropping, the force acting upon you as you go down the slide is dropping, the acceleration is dropping. It's not constant. It means you can't use any of the kinematic equations anymore. And that's why this law for conservation of energy is very useful, because you can still solve for quantities that are of interest, like how fast is it moving at the bottom of the slide, without using Newton's laws, without using vectors, and without using any of the kinematic equations. So this is the bottom of it, V final. We're wondering what that is. And we know that starts up here with initial velocity of 0. You would need to know how far it falls, h, and you reference the idea that conservation of energy means that the initial energy at any given point you choose has to be equal to the final total energy at any given point you choose. Remembering that E is the total mechanical energy. It's the sum of any potential or kinetic energies that exist at a certain point. It's your total energy. It's not just your kinetic or your potential. E is your total mechanical energy. And so often you would just show that, okay, there might be some initial kinetic energy and might be some initial potential energy. And if there is, when we add those together, that's representative of the total mechanical energy. And that we can make a similar statement for the final point that we choose, and recognize that the sum of kinetic energy plus final energy, the sum of the kinetic energy and potential energy at the final point is representative of the total mechanical energy at your final point. Where's your initial point? Right here. Where's your final point? At the bottom of the ramp, the bottom of the slide. If you start out with no initial velocity, that means your initial kinetic energy is 0. Because kinetic energy is 1/2 mv squared. And if v is 0, you've got no motion energy. So that gets crossed out. And then you notice that bottom of the ramp, when you're down here, you have no height. Your final height is 0. And since potential energy is gravitational potential energy, mgh, if your height is 0, then you've got no potential energy at the bottom of the ramp. That's gone. Then you just stick in expressions, mgh initial must be equal to your final kinetic energy at the bottom of the ramp. It's stating that whatever your initial potential energy was, if there was no loss of energy through friction, no loss of energy through air resistance, which in our real world is completely untrue, but if this was a very idealized problem where all those frictional forces are removed, and you started up here at the top of this ramp with 100 joules of potential energy, then how much kinetic energy will you have at the bottom of the ramp? 100 joules. All of that energy is going to get turned into motion energy. Remember, the potential energy is stored energy by definition, and therefore it will turn into kinetic energy. And so that's what this equation is saying. It's saying whatever the amount is, maybe it's the number 100, who knows what it is, we'd have to multiply m by g by h to get out whatever that number is, that the kinetic energy is going to be that same ultimate number. All of it's going to get converted over to kinetic energy. Notice that that mass cancels, means it doesn't matter what the mass of this object is. And if you're solving for the final kinetic energy, as comes up in a lot of problems, you get this very well-known equation in physics. Although I made a mistake, it shouldn't be h final. It's equal to the square root of 2g times your initial height, whatever that initial height is on the top of this ramp. And so you calculate how fast something is moving at the bottom of a ramp by multiplying the initial height by g by 2 and square rooting it. And that gives you the final velocity at the bottom of a ramp. Okay, conservation of energy. I'm going to just puzzle in my head to think if there's any last minute things I need to comment on. It's a very, very quick overview, but that was the intention of these lessons. I went over Hooke's law, I went over potential energy in a spring. I guess we'll just we'll finish this here. I'll probably do one more. I'll do one more after this with simple harmonic motion, and we'll go from there. All right. Hopefully that was useful for everybody.